Let's refresh our memory on the bipolar junction transistor before we start talking about FETs. So the BJT had 3 doped semiconductor regions, and they were physically connected at a junction. And it's a bipolar junction because it's the joining of an N and a P region. The BJT is essentially a current-to-current amplifier. We inject a current into the base, and we get a larger current flowing from collector to emitter. How much larger? It's beta times larger. Beta is the multiplying factor, and it's a reasonably linear factor, especially if you operate over a small region. If we want to use an NPN BJT in a circuit, we would do so like this. We would inject a current into the base that would draw more current down this way, and so the voltage at this point would fall. If we inject enough current, we would operate that transistor like a switch, and in this example here with an NPN, it would be a switch to ground, and that turning on the switch would reduce the voltage to 0. From a 2-port model, we think of it as we inject a current IB in here, and we get a larger current flowing from collector to emitter on this side. How much larger? Beta times larger. Now, I've drawn this 2-port model with an input and output side, but if you remember from my previous lectures, I said that you could join the 2 of them together internally and bring them out 1 pin, and then that represents a 3-terminal device of a transistor. We can develop a family of characteristic curves for the transistor that describe its operation by applying a voltage to the collector and then testing it at different base currents. And this builds up the family of characteristic curves. What we can do is from this graph, if I draw a line down here and I basically take the IBs, I take the base currents at each of these points, I can figure out what the base current is, and I can figure out what the collector current is, and then I could graph that as well. I could create a graph of IB versus IC. And I've done that over here. Here's IB on the horizontal, and here's IC on the vertical. And if I transfer all of these points over and then draw a line between them, you can see that it's pretty much a straight line. This says that the transistor is a linear device. The gain is fairly linear over the range of operation, as long as the range isn't too big. We call this the small signal gain. If you get a huge gain and you're trying to sweep a large voltage, then you'll run into some non-linearities. But over a narrow region, it's a really linear device. The field effect transistor also has 3 doped semiconductor regions, but the terminals that come out of the package we refer to as the gate, the source, and the drain. The main difference between a FET and a BJT is that the gate is an insulated gate. And what I mean by that is that the aluminum plating that represents the gate is physically separated from the P-type body of the transistor by an insulating layer of glass. So here you can see that the gate terminal is physically separated from the internals of the transistor. Now what that means from a functional standpoint is that the field effect transistor cannot be a current amplifier. If it's an insulated gate, then the amount of current that flows into the gate must be equal to 0. What this means is that the FET will actually convert a voltage to a current. It's a voltage applied to the gate between the gate and the source that results in a large current flowing from the drain to the source. Now, one of the things about a FET that makes it more difficult to analyze is that the response is parabolic. The drain current is a function of the input voltage squared. This means that in order to solve for the operating point, you have to solve a quadratic. So pretty much all semiconductor courses start with BJTs, and then you learn how to solve for an operating point because it makes the math easier because it's linear. Now we can develop a family of characteristic curves for the FET in much the same way that we did for the BJT. So here, this VDS over here, this would be the voltage across the FET. And then over here we have drain current, that's the current through it. So it's the voltage across versus the current through at different gate voltages. So here you can see we're increasing the gate voltage from 5 volts to 6 volts to 7 volts. And one of the things that you can see is that with the FET, every time it increases by a step of 1 volt, here the distance between the two currents is this. But as we go to the next voltage, you can see it's actually a larger current jump on the drain, and again a larger current jump. And down here you can see it's really small. So what this implies is that there's a parabolic response between the gate voltage and the drain current. And so we can take these points here and we can transfer them over to a diagram that shows the voltage applied to the gate versus the current through the drain. And we can see that it is in fact parabolic, that as you increase the gate voltage, initially it's very small and there's no drain current, but then once you get beyond a certain threshold, then it starts to increase rapidly and it goes parabolic. So the drain current is a function of VGS squared. Let's talk about the theory of operation of FETs by starting with the enhancement mode N-channel MOSFET. Now, in its unbiased state, when we say unbiased, we mean that it's got a gate voltage on it that results in no drain current. And the gate voltage that results in that is a VGS of 0 volts. How do we get that? We basically take a wire and we short the gate to the source, and that gets us VGS equals 0 volts. And then we will have no drain current. Now, essentially in this state, the FET acts the same as a BJT. It has 3 doped regions. It has 2 ends separated by a p-type region, and when it's unbiased, those regions are essentially acting like 2 back-to-back diodes. So there's one diode, and here's the other diode, with the P in the middle and the N types on the top and bottom. And in this state here, 2 back-to-back diodes will give you a drain current of 0 volts. So that's unbiased. How do we turn this into a biased FET? In order to do that, we need to apply a gate voltage. So we remove the short and we replace that with a positive voltage source. Now, although the majority carriers in a p-type region is holes, that doesn't mean that there aren't electrons in there. It just means that there's more holes than there are electrons, and that's where most of the current is. If I apply a positive voltage to the gate, then what's going to happen is some of those electrons are going to get attracted to the positive charge on the gate. And if enough of them come over to that area, then what will happen is that we will see an N-channel, an N-type region form at the gate of the FET on the other side of the silicon dioxide layer. And if enough electrons form, then what we will have is we'll end up with a continuous channel from the drain to the source, and we will have conduction. If we apply a larger voltage onto the gate of the FET, then we will draw in more electrons, and the gate will widen. The N-type region at the gate will widen, and we'll get more conduction. So let's summarize this. So the N-channel enhancement mode MOSFET. It's initially an insulator, and the application of the correct gate voltage draws in electrons until an N-channel is formed. This is called enhancement mode. When it turns from an insulator to a conductor, we say that the gate voltage enhances conduction. Now, an N-channel MOSFET can be used essentially in the same types of circuit configurations that we use an NPN transistor. We can use it as an amplifier, and we can use it as a switch. When we talked about bipolar junction transistors, we learned that there was two basic types. There's a PNP and an NPN. Similarly, FETs have two basic types. There's an N-channel FET and there's a P-channel FET. So now we're going to talk about the P-channel FET and how that operates. So like the N-channel FET, initially in its unbiased state, we have an N region which is separating two P-types. So there is no channel in its default state. We would get the default state by saying that VGS is equal to 0 volts. And we would achieve that by shorting the gate to the source, which I've done here. And you may have noticed that I've shorted it to the upper terminal. That's because when we look at P-channel FETs, they're flipped vertically. The source is at the top and the drain is at the bottom. So we would set VGS equals 0 volts by shorting the gate to the source, and then there would be no P-channel and we would have no conduction. We would create a channel by putting the correct voltage on the VGS, and we would apply a voltage like so. We'd apply a negative voltage to the gate. This is positive and this is negative, and so VGS in this case would be a negative voltage. And so we'd put a negative voltage on the gate here, and that would push the electrons out of this area, and it would draw in the holes, or it would create holes by ejecting the electrons out of the area. And if I had enough holes between the two P-type areas, then I would create a P-channel between those two areas, and now I have a continuous channel of carriers from source to drain, and I would get current to flow. So the enhancement mode P-channel MOSFET works by creating a P-channel of charge carriers. A negative voltage is applied to the gate, and that pushes away the electrons, creating a P-channel from source to drain. The N and P-channel enhancement mode MOSFETs are the world's most common transistors. So I want to talk about depletion mode FETs, and we'll talk about this. We'll start off with the N-channel depletion mode FET. Now in this kind of a FET, the channel is already there, so there's already a doped N-type material from the drain to the source, so that even if the gate voltage is 0, so if the gate voltage is shorted out, you will still get current flowing from the drain to the source in its normal operation. So this is like a normally closed switch, and what you can do with a depletion mode FET is you can do one of two things. You can put a positive voltage on the gate so that you enhance the conductivity of the part, or you can put a negative voltage on the gate to decrease its conductivity and turn it off. So this is a normally on part. The depletion mode FET is normally on, and with the right gate voltage you turn it off. So let's look at a situation where we want to enhance the conductivity. So if we put a positive VGS on the gate, then we will be putting a positive charge on the gate of the FET, and this will attract electrons out of the P-type region. There is electrons out there. They will be attracted in towards the gate, and you will enhance the conductivity of the gate, essentially thickening it up. If you continue to put on positive charge, then it will get enhanced even a little bit more. So a depletion mode FET, you can enhance the gate in order to improve conductivity, or you can deplete the gate carriers in order to minimize it. So to deplete the gate carriers, what we would do is we would put a negative voltage on the gate, like so, and that would put negative charge on the gate, which would then push electrons out of the N channel region. So we push electrons out of this region, and you would end up with this area turning into a P-type region. So you would narrow the gate down, and if you continued to put a negative voltage on it, at some point you're going to pinch the gate off, and you will have no conduction. So the depletion mode FET is normally conductive, and if you apply a negative VGS, you will turn it off. And there is also depletion mode P-channel MOSFETs. And these ones are a depletion mode device, so that means that the channel is present in the unbiased device. If I apply a 0 voltage to the gate, if I short the gate to the source, I will have a channel which is embedded into the part at manufacture, and I will get current flowing through that channel from source down to drain. Now the depletion mode device, what we can do is if we apply an appropriate voltage, depending on what voltage we apply, we can either turn the channel completely off, we can deplete the channel, or we can enhance the channel. So here, this is the source up over here. This is the drain. Now P-channel FET, if we put a negative voltage on the gate, we will enhance the channel. So if I put a negative voltage, let's say I take this and I tie that to ground, and now there is a negative voltage. Ground is 0 volts. The source is sitting at a high side, let's say 12. So the VGS in this case is minus 12 volts. The gate source is a negative voltage. This will repel electrons out of the gate area, and it will then have some holes that are left behind. So we will effectively enhance the channel, we'll widen the channel, making the device more conductive. If a negative VGS widens the channel and enhances conduction, then a positive VGS should narrow the channel and deplete conductors. So let's see if that happens. So let's say the gate, we take the gate and we make it more positive than the source. Then what will happen is this will become positive in this area, and it will draw in more electrons. So the electrons will come into this area, and that will fill up the holes. So it'll deplete the carriers in that area, and we will essentially narrow the channel because we will make it, we'll bring it in and we'll increase the size of the N region, and we'll narrow that channel until finally we'll have depleted all of the carriers and it will no longer conduct. So the depletion mode MOSFET, the channel's present in the unbiased device, it's normally a conductor, it's like a normally on switch. By applying the correct gate voltage, you can enhance conduction or deplete the channel until it doesn't conduct at all. So overall, there's 6 different field effect transistors that break down into 2 categories. There's the junction FETs, which we haven't talked about yet, and then there's the metal oxide semiconductor FETs, which we have. Now the metal oxide semiconductor FETs, the short form for that is MOSFET. So that's an acronym attached to another acronym. They break down into 2 categories. There's the enhancement mode, where the part is normally off and the gate voltage turns it on. And then there's depletion mode, where the part normally conducts and you can turn it off with the gate voltage, or you can actually make it conduct better. And each of those, the depletion mode and the enhancement mode, break down into a further 2 groups, which is an N channel and a P channel. Let's take a look how you would identify these in a schematic. So you can take a look here and you can see a couple of things. First thing I would look at here is if you look at this one, you can see that here's the gate and there's a gap between the gate and these 3 bars. That implies that this is an insulated gate FET and that there's an oxide layer between the gate and the body of the semiconductor. Now the 3 bars on these 2, what that's telling you is that this is normally a broken channel, and when you apply the correct gate voltage, you're going to form that channel, and then you're going to have conduction. So this is the normally open circuit FETs. These 2 are the normally open circuit, and then when you turn them on, they start to conduct. And then the last thing that you'll notice that there's a little diode here, and that little diode tells you the polarity of the body diode within the FET. So this one here, this is the N channel. So we would say that that one starts off with 2 N channels in a P substrate. So the body diode would be from P. The body diode would normally go from the P type to the N type. So this diode that we draw here, it's pointing towards the gate, and that's how we see it in the schematic. So in the P channel FET, the body of the part is doped as an N-type region, and then there's 2 P channels in it, and then you're going to create a full P channel between the 2 P types. So in this one, the diode that normally sits inside the part is a diode between the P type here and the N type over here, so that diode points away from the gate. So the diode arrow within the part is telling you which way the internal diode created between the terminals and the body of the part. Now on the depletion mode parts, the big difference is that the gate is drawn initially as a complete line between drain and source, implying that the channel is normally there, and then when we apply the gate voltage, we can deplete it or enhance it. Now the JFETs, the last one here is the JFETs. And the JFETs are a junction FET. They actually don't have an insulated gate, so the gate is actually connected straight to the body. These can only be used in a certain voltage configuration. I think you'll learn more about that in maybe your next course. So I want to wrap this up by telling you what I think are the top 10 things that you should know about field effect transistors. So number 1, the world's most common transistors are the N-channel and P-channel enhancement mode FETs. This is what's used in your microprocessors, so there's billions of these in a single chip in a modern day computer. A FET is an insulated gate transistor. That means that there is no gate current, and it also means that the 2-port model of a FET is a voltage-controlled current source. Since there's no gate current, this cannot be a current amplifier. Beta is not the value you use to figure out what the output current is. The multiplier that you would use to convert the input voltage to an output current is a conductance factor, and we call that GM. That's the name that's given to it, and the units are in Siemens because it's amps per volt. It's how many amps do I get out for every volt of input. How do I use these in circuits? Now the N-channel MOSFET can be used in the same manner as an NPN transistor can. That is both in an amplifier and a switch. So you would use it in an amplifier on the low side of a push-pull amplifier, or you would use it as a switch to ground for a switching device. The P-channel is used in the same manner as the PNP transistor. So you would use it for the high side in a push-pull amplifier, or you would use it as a high side switch in a switching device. FET amplifiers work pretty much the same way as BJT amplifiers. You get the same efficiencies, the same power dissipations in the transistors, and you get a very similar output. The biasing is a little more difficult with FETs because it's a V-squared device, but once you've got them biased and centered on the load line, you get pretty much a linear output in a small swing and a very similar output to a BJT. It's only until you try and go from the full swing output that you start to see some nonlinearities. Number 8, FETs make awesome switches. I can't say this enough. This is probably the number one application of FETs, is that they make way better switches than BJTs, and I'm going to explain that in a subsequent video. Number 9, when you're using them as a switch, the most important characteristics are VGS threshold and RDS on. That's when it starts to turn on and what it turns into once you've turned it on. And number 10, don't forget that the schematic symbol tells you a lot about what kind of FET you're looking at. You got to look for the 3 bars on the channel instead of a solid channel, and you'll look for the insulated gate symbol and the direction of that diode, and from that you can figure out what kind of FET you're looking at.